Okay, here recording in progress, so we'll share the screen. Okay, we're getting very close to the end. My original schedule, I wasn't supposed to start 11.8 until today. I'm already finished with 11.8. So we're going to do 11.9. In fact, we have 3 weeks left, sort of. This is a short week, and we have 3 sections left. So we'll be done in plenty of time, which means all the sessions are probably going to be done early. So 11.9 today and tomorrow. You get your quiz on Wednesday because we have a Thanksgiving holiday this week. So give you the quiz on Wednesday. It's due 11:59 p.m. Wednesday. Then we're off for Thanksgiving. Okay, and then we just have 2 weeks after that. And I'm going to go ahead and declare the most likely scenarios we will go ahead and have on the original schedule the exam 5 on Thursday the 9th. That just gives us an extra day because I think we're going to be finished quite early. So let's aim right now for the 9th. If something goes wrong and I have to push it back to the 10th, that's still going to be okay. Okay, now, once again, if I give you the test on Thursday the 9th, it doesn't mean I'm going to finish it all and give it back to you by the next day, but I will at least give you the solutions. So I'll have the solutions video for you so you can start studying for the final exam. Then your individual test, I'll give it to you hopefully over the weekend like I normally do. Okay, and then all we have after that is our final exam. Please notice our final exam is on the 17th. So after Friday the 10th, we do not meet the following week. It's final exam week. We don't meet until Friday. So we don't meet Monday, we don't meet Tuesday, we don't meet Wednesday, we don't meet Thursday. Our final exam is Friday the 17th, 8:10 to 10:40 a.m. I do have office hours during finals week. It's basically 8 to 10 a.m. Tuesday, Wednesday, Thursday, but not Monday. Monday, I have to give another final exam. So if you want to catch me during office hours, use the same Zoom link, that we've been doing for the exams. Because that'll be the 14th, 15th, and 16th during finals week if you want to catch me during that time. And I just noticed that this thing is frozen now, so I'll have to unfreeze and freeze again. Let me see if I can get back in. Sorry about that. So we're having a break. So let me try this, unplug this. Like that. And let me try to share the screen again. Okay, looks like we're back in business. Just get it to be the right way. All right. And as usual, you should have gotten an email back from me from your most recent quiz. That was out of 5 points, as quizzes always are. And I sent out the solutions video also. So if you did not get it back from me, then let me know, holler and scream at me about that. Okay, and be prepared for the quiz coming quickly. It's a very short week, only 3 days this week, and then we have a nice Thanksgiving after that. Then once that hits, we only have 2 weeks left before the semester is over. Okay. All right, so I'm going to get started with 11.9. There is actually something in 11.10 that I want to show you, and that will be part of the quiz. In my opinion, this week's quiz is fairly easy. It's pretty much just using your calculator. You're just going to do some calculations, but it does illustrate what I'm trying to show you. Okay, so let me go ahead and give you that. So on 11.10, even though I'm not lecturing on 11.10 per se, at least not yet, but let me show you what you want to put down on your formula sheet. This is from 11.10, page 768. There are all these formulas for power series. Okay, so 768. You'll want to do the first 5. You don't need these so much. I mean, they're true. Let me just draw a line here. How's that? Okay, so you want to know these. Put these on your cheat sheet, on your formula sheet. Okay, it's a power series. It's called a Maclaurin series. I'll talk more about that later also. But there's a power series. These infinite polynomials for 1 over 1 minus x, which I'll talk about today, and e to the x, sine x, cosine x, and inverse tangent of x. These are the big ones for me. These two, they're true. There's nothing wrong with them, but I'm not going to emphasize them. In fact, I'm hardly going to look at this one at all. This one was sort of derived. I may even derive some of that today. Okay, but here are power series. Notice they look like polynomials, right? In fact, for all of these, if I took out the dot, 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 right? So, oh, that looks like a third degree polynomial, a polynomial. But in these cases, you just keep going. It goes on forever, right? So there are the formulas for these. Okay, so we have a formula, nice formula for sine and cosine. You might be wondering, what about all the others? They're there, but they're not as heavily emphasized. Notice that tangent's not there, but inverse tangent is, surprisingly. Okay, inverse tangent has a nice representation, but tangent does not have a nice representation. Okay, and the radius of convergence for these, that's 1. These are infinity, and this one is just 1. Okay, again, you should be considered fortunate. The last time I taught this class, I made them memorize this. Okay, and I gave memory tricks, how you would memorize it, but whatever. Okay, you're actually going to be using this on the quiz on Wednesday. So even though I may not get to section 10, okay, you'll be using this. It's pretty much just calculator work for these. Notice they look like infinite polynomials, right? Polynomials of degree infinity. They just go on and on and on and on and on. Okay, so please make a note of this. It's on page 768. You're welcome to put these on your cheat sheet. You don't need these last two. Okay. All right, so we'll begin section 9. Representation of functions as power series, page 752. Okay, so just giving you an introduction to some stuff right now. We may not do very many problems today, but that's okay. Excuse me. Okay, recall we have our geometric series where the sum is a over 1 minus r. A is the first term, r is the common ratio, and absolute value of r is less than 1, right? That means r is between -1 and 1. Okay, so that means if I have 1 over 1 minus x, that looks like this, right? The first term is 1, the common ratio is x. So I put down a 1, and then if it's geometric, I just keep multiplying by x. So plus x squared plus x cubed and so on. Okay, writing it in summation notation, it's summation n equals 0 to infinity of x to the n. Okay, and we know the radius of convergence is 1 because this is a geometric series. So a geometric series converges if the thing behind my pen is less than 1, which means x is between -1 and 1. Okay, so radius of convergence is 1 in this case. Okay. Now, for 1 over 1 plus x, which happens to be problem number 3, well, we have to force this to look like this. So 1 plus x is 1 minus a negative x, right? 1 over 1 minus a negative x. So now that looks like a geometric series where the numerator is the a, 1. The common ratio is negative x. So I keep multiplying by negative x, which will make it alternating. Okay, so 1 minus x plus x squared minus x cubed plus dot, dot, dot. Okay, let's set the ground rules for how you write the answers for me. I think I've mentioned it before, but say it again here. The final answer for the series show at least 4 terms. The key thing is for the final answer. I may have to write 5, I may have to write 6 in between so that the final answer has at least 4 terms. I know that doesn't make a whole lot of sense right now, but we'll see what I mean by that. But in some instances, you don't want to stop after 4 series because you end up differentiating, and when you differentiate, a constant drops out. So then instead of 4 terms, you would have 3. And I'll show you what I'm talking about in those kinds of instances. Okay, and while I'm at it, let me go ahead and show you all the homework problems. Again, for the benefit of those of you who don't have the book and aren't getting it. So we are here, 3 to 33 odd. 3 to 33 odd. Okay, page 757. Okay, so if you're not getting a book, 3579, 11, 13, okay, 15 through 19, whoops. Okay. Then the next page. Let's see, we said go up to what, 33? Right, 11.9 up to 33. Okay. So page 758, 21, 23, 25, 27, 29, 31, 33. Okay, they're all there. Fine. Yeah, let me show you this theorem on page 754. Okay, this box here, box 2, everything in that box you want. Okay. Looks scary. There's a lot there. Let me hit the highlights. If you have a power series centered at x equals a, we talked about before, centered somewhere. We like it when it's just x to the n, then you're centered at 0. Here you're centered at a. Okay. If it has a radius of convergence of r greater than 0, this sounds scary. It basically means you can differentiate term by term. So how do I differentiate infinitely many terms? Just differentiate every single one. Okay. How do I integrate? You just integrate term by term. Okay, so if you look at all this, so what's all this stuff? It's just a derivative of all these guys. And if you integrate, you just integrate term by term. Okay. The radii, plural of radius, one radius, two radii, of convergence of the power series are both r. So if you have a certain radius of convergence of a power series, so how do I take the derivative of infinitely many terms? Just differentiate term by term. How do I integrate? You integrate term by term, okay, and you will have the same radius of convergence. That's a little bit tricky. You don't necessarily have the same interval of convergence, okay, but you'll have the same radius of convergence. Okay, so remember last time we were doing the interval of convergence, right? So we said in general, you have a number line, the stuff in between, you have absolute convergence, the stuff out here, you have divergence, and then the two endpoints, you could have open, 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 close, close, open, or close, close. Okay. After you integrate or differentiate, you have the same radius convergence. So all the in-between stuff, they'll still be absolutely convergent. These two will still be divergent, but you don't know anything about these endpoints. It could go from convergent to divergent or divergent to convergent, or they could both be convergent or they could both be divergent. All of those are possible. Okay, so you have to, after you differentiate or integrate, they're just polynomials. They look like polynomials, albeit infinite polynomials, but they're essentially polynomials. So the stuff in between when you have absolute convergence, it'll still be absolutely convergent after you integrate or differentiate. The stuff out here, which diverge, it'll still diverge. The only question mark are these two endpoints. Okay. It could go from convergent to divergent. It could go from divergent to convergent. It could be convergent and stay convergent. It could be divergent. It can stay divergent. All of those are possibilities. Okay. Actually, for now, we're mostly not concerned too much about what happens to the endpoints. We're just worried about the radii of convergence. Okay. Okay, so I've essentially already done problem 3 for you right here. Now, here's a nice thing. So we have 1 over 1 plus x is 1 minus x plus x squared minus x cubed, and so on. Okay. So if I want the integral of 1 over 1 plus x dx, which I know how to do, I can also write it as the integral of this infinite series, 1 minus x plus x squared minus x cubed plus dot, dot, dot dx. How do I integrate? Just integrate term by term. And the nice thing about these infinite polynomials are very easy to differentiate, right? You just use the power root, and they're also very easy to integrate. Okay, how do I do the left-hand side? That's ln absolute 1 plus x. Now, this is an indefinite integral. Usually for indefinite integrals, you would put blah, blah, blah plus c at the end. So what do you do if you have infinitely many terms? There is no n. Well, we put the c in the front. So notice to go c plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. Okay, and by the way, you might be wondering, how come I don't put a plus c1 and c2 on this side? It's almost like the section we did on differential equations. You could say ln absolute 1 plus x plus c1, and this is c2, but you would put them together as a c anyway. So normally you don't have to worry about one of the sides. So we leave this side alone, and only on this side do we put the c. And the radius of convergence stays 1. The radius of convergence over here was 1, so the radius of convergence stays 1. Now, to find the c in this case, let me plug in 0. Put a 0 here, ln1. Put a 0 here, c plus 0 minus 0, these are all zeros, right? So ln1 is c, or c is equal to 0. Okay, so I have ln absolute 1 plus x. Yes, I know I wrote parentheses here, but temporarily pretend its absolute value of 1 plus x is equal to this. So this is a power series representation of ln 1 plus x, which happened to be the 6th formula down in the thing I just showed you. Back on page 768. The 6th one down, the ln 1 plus x, the one that I said you didn't have to worry about. Okay, there it is. Okay, right, is -1 to the n minus 1 x to the n over n. That's what we've got over here. So it's optional, you can put it or not. Okay, you can always derive it by doing this. Now, what allowed me to drop the bars? Well, the radius of convergence is 1. That means x is between -1 and 1. The absolute smallest I could be is -1. Well, if I have -1, I'm doing ln of 0, which doesn't make sense anyway. Okay, if I take any other number between -1 and 1, this is always positive, right? So since it's always positive, drop the bars. So I have this. So ln 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, which means that is a way, that's not the only way, but that is a way I can compute the natural log function. Okay. In case you're wondering, the nice thing about what we're learning here is sometimes you ever wonder, how do you program the calculator to do all of our fancy formulas, right? How do you get the calculator to do sine and cosine and ln and all that stuff, right? I mean, what's behind the scenes? What's back of those chips there? I mean, for us, we just push the button and say, oh yeah, I just punch sine of 2 radians and it magically comes out to be whatever, but how do you get it? How does a calculator come up with those responses? Okay, so like when I do ln2, right? ln 2.6931, whatever. What does the calculator actually do? How did it get that number? Or what else? Okay, so a way, I'm not saying it's the only way, but one way to do it is this. For instance, this. Okay. Now, I did just type in ln2 for a reason, because I knew I was going to come up with that. So how does a calculator do ln2? How does it get 0.693, whatever? Okay, let me plug in 1 right here. Plug in 1, I get ln2, right? 1 minus a half plus a third minus a fourth plus dot, dot, dot. You recognize that? That is our alternating harmonic series. Okay, and in a section previously, I said we're actually going to come back to the alternating harmonic series and prove that it's a natural log of 2. Okay, and I said we would show that later. This is later. I'm now showing you where it comes from. So very nice formula. Okay, and then the interesting thing is ln, right? You say this ln is so weird, it's such a strange function. There can't be a nice formula for it. Oh yes, there is. 1 minus that. I mean, you understand the pattern. The denominators just go 1, 2, 3, 4, 5, 6, 7, just do all the positive integer and you just make it alternating. And believe it or not, that will converge to the natural log of 2, which is 0.6931. Okay. And furthermore, by the alternating series estimation theorem, okay, if you stop anywhere, the error is no more than the next term. Okay, so if you were to program a computer to do this, right, and have it do millions of terms, which is very easy for a computer to do, you or I as human beings don't want to do that, but computer can do that easily. You'll see it becomes this 0.6931 or whatever. I mean, we can look at part of this. 1 minus a half, that's 0.5, right? And 0.5 plus a third is like, 0.83 or whatnot. Okay, and then I take away a fourth, that's like 0.58. Okay, so it does seem to converge as we would. So here's a nice formula for natural log of 2. You don't have to memorize that, but it's just something interesting I thought I'd show you. Okay, next interesting thing I thought I'd show you is this. Okay, let's start with 1 over 1 plus x squared. 1 over 1 plus x squared, which I can write as 1 over 1 minus a negative x squared. Right, I'm trying to make it look like a over 1 minus r. Right, so the first term is 1. The common ratio is negative x squared. So 1 minus x squared plus x to the 4th minus x to the 6th. Okay, that fits my rule of having at least 4 terms. And now let me integrate both sides. Integral of 1 over 1 plus x squared is the integral of all this stuff dx. Well, what's the integral of 1 over 1 plus x squared? That's my inverse tangent function, right? Inverse tangent is, okay, it's an indefinite integral, so I need a plus c. You say, well, you can't put it at the end because there is no end, so put it at the beginning. C plus, then I integrate term by term. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. Okay, radius of convergence again is 1. Okay, if there's a geometric series, okay, then the thing behind my pen has to be between -1 and 1. Negative x squared in absolute value is less than 1. That's the same thing as saying x squared is less than 1, which means x is between -1 and 1. Now, let me plug in 0 again. Put a 0 here, 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 here. These are all gone. That's gone. You would have inverse tangent of 0 is c plus 0 minus 0 plus 0. And the inverse tangent of 0 is 0, so c is 0. So I've derived a formula for inverse tangent of x. Inverse tangent of x is x over 1 minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. And that happens to be this one, right? On page 768. So I've derived for you that bottom one there, inverse tangent of x. Okay. And they wrote it as a nice series fashion, summation n equals 0 to infinity. Notice all of these are starting at 0 for the most part, right? N equals 0, 0, 0. Okay. Well, they don't do that for the natural log because you cannot plug in 0, but be that as it may. Okay, so it looks like inverse tangent of x is -1 to the n, x to the 2n plus 1 over 2n plus 1. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. Okay, so here's a formula for inverse tangent. Put it on your cheat sheet. Okay, again, side note, the last time I taught this class, we were face to face. I made him memorize it, but I'm not making you guys memorize it since we're under COVID. Okay, now here's something that's really, really nice, I think. Plug in 1. Inverse tangent 1. 1 raised to anything is 1, right? So 1 minus a third plus a fifth minus 1/7. But we know the inverse tangent of 1, don't we? Inverse tangent of 1 is pi over 4. So pi over 4 is all that. Multiply both sides by 4. Okay, so you've maybe seen, you can look it up on the internet. There's millions of digits of pi. You might say there's no rhyme or reason, there's no order to pi, there's no nice formula. Oh, yes, there is. Take a look at this, very easy to follow. Pi, believe it or not, is 4 times 1 minus a third plus a fifth minus 7, right? Just have odd denominators, make it alternating. Okay. We know this converges by the alternating series test. It's alternating, terms decrease in absolute value and approach 0. And I should have said that over here also for LN2, but we already knew that it was an alternating harmonic series. It's alternating, terms decrease in absolute value and approach 0. So we know the series converges. Okay, so likewise, here's an infinite series. 4 times, well, you can just make all the numerators 4. 4 minus 4 thirds plus 4 fifths minus 4 sevenths. Okay, it's alternating, terms decrease in absolute value and approach 0. Therefore, the series converges. Believe it or not, that series converges to pi. Okay. And yes, you could program your calculator or computer to do this to millions of terms. You or I don't want to do that, but millions of calculations, that's very easy for computers nowadays. And you'll see 3.14159, blah, 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 blah. Right. So we have a nice expression for pi. And so I thought, I wanted to show you. So one nice thing about this class, Calc 2, you get the derivation of a lot of our geometric formulas, right? So we've derived the formulas for the volume of a sphere, right? Surface area of a sphere, volume of a cone, circumference of a circle, area of a circle, all those things. And we've seen nice formulas for natural log of 2, and a nice formula for pi. And very shortly, well, it's got to be shortly because we're running out of semester, but very shortly, a nice formula for E also. Let's see. Okay, so I'll get started doing a couple of problems and then won't go much longer, then I'll quit. All right, so problem 5, please. All right, so I already did 3. 5, find a power series representation for f of x equals 2 over 3 minus x. Okay, determine the integral of convergence. Okay, so 2 over 3 minus x. Okay, I have to force this to look like a over 1 minus r. So I factor out a 3. Okay, so if I take out a 3, I'm going to go 1 minus, and then you may have seen this trick before, maybe in your trig class. If I have to multiply by 3, I divide by 3. Okay, so 2 over 3 parentheses 1 minus x over 3. Okay, now I don't have any more hands. I need one finger for this and one finger for this, but multiply the 3 out. Do you not get that back, right? 3 times 1 is 3. 3 times negative x over 3 is negative x. So they are equivalent. And then divide top and bottom by 3, like that. So I have this funny looking thing. 2/3 over 1 minus x over 3. This is equivalent to the original. Okay. But I forced it to look like a over 1 minus r. Okay. By the way, if you want to double check the algebra, well, multiply top and bottom by 3. If you multiply the top by 3, you get 2, right? And what happens if you multiply this by 3? You get 3 minus x. So it matches. But why would I ever want to write it this weird way? Because it now looks like this. So that means the numerator is your first term, and the common ratio is x over 3. So we go 2/3, then multiply that by x over 3, 2x over 9. Multiply that by x over 3, 2x squared over 27. Multiply that by x over 3, 2x cubed over 81, plus dot, dot, dot. Okay, so this fits my rule, just put down 4 terms. For now, unless I say otherwise, you don't have to write the summation formula for that. Okay, just write it like that. Okay, radius of convergence. We know that x over 3 has to be between -1 and 1. So I've written down here -1 less than x over 3 less than 1. Multiply everything by 3, and you have x between -3 and 3. So the radius of convergence is 3. Okay. And I'm not going to worry too much about interval of convergence. I mean, you would plug in, well, you certainly can't plug in 3 because you're dividing by 0. Okay. And I think you can also show if you plug in -3, you also get something messy, but we're only going to worry right now about radius of convergence, not interval of convergence. Okay. Yeah, let's see, 7 star, and then I'll stop. Just get you the technique. X over 9 plus x squared. Okay, write it as this infinite polynomial power series. Okay, so the trick again is to factor out the 9. So you go 9 parentheses 1 plus, if I have to multiply by 9 here, I'm going to divide, make it x squared over 9. Okay, so x divided by 1 plus x squared over 9. And then divide top and bottom by 9. Similar to this other one. So x over 9 over 1 minus a minus x squared over 9. Okay, can you see that this is the same as that? If you're not convinced of that, let's work it out. Okay, of course it's a plus, double negative. Now if I multiply top and bottom by 9, 9 times that is x, 9 times 1 is 9, 9 times that is x squared. So it works. But I made it look like a over 1 minus r. So by formula, you got to have a 1. So you say, what if there isn't a 1? I force it to be a 1. And what if there's a plus? Make it a minus minus, right? So that's the trick. Whoops. Okay, so first term is x over 9, and now I keep multiplying by negative x squared over 9. So multiply this by negative x squared over 9, negative x cubed over 9 squared. Multiply that by negative x squared over 9, positive x to the 5th over 9 cubed. Okay, yeah, these numbers get so big, you don't have to actually work them out. Just keep it as 9 squared, 9 cubed. Multiply that by negative x squared over 9, minus x to the 7th over 9 to the 4th, plus dot, dot, dot. So there we are, 4 terms. Radius of convergence. So the thing behind my finger has to be between negative 1 and 1. Okay, drop the negative. So that means x is between negative 3 and 3. So the radius of convergence is 3. Okay, so that's as much as I was going to go over today, unless you had any questions. So I know I just barely got started with doing problems, but I wanted to give you all the introductory material and those neat formulas for sine, cosine, inverse tangent, stuff like that. Okay, but otherwise I will stop the share and see if you have any questions, and if not, we're done. Okay, so let me check the chats. I don't see anything. So any questions, please? All right, we're done for today, folks. So that's it. Have a good day, and we'll see you next time. Okay, bye, everybody.